All right. Good evening, everyone. And thanks for joining another NYJavaSIG event. We're very happy to have you here with us. This is a special event. Last week, Java celebrated its 25th anniversary. So we have a special event tonight. We have all of our NYJavaSIG members here with us. It's a pleasure to have you here. Please, if you're not following us on the social network, here's our contacts: Twitter, NYJavaSIG, our YouTube channel. Join, subscribe, follow us. The more followers we have, more people we can bring and share experience with you. So today, we would like to ask our members here about Java, what Java means to you. Frank, you have created NYJavaSIG 25 years ago, right? The first Java user group. So please share with us what Java means to you, Frank.
Well, since I started 25 years ago, it means one thing. It means that I'm old. So certainly there's a lot of cool technical features about Java over the past 25 years, and now more features coming faster than we ever thought of before. But I think the biggest thing for me is that I've made so many friends. It's a Java community. I made many friends over the years, and many of them are really close friends now. So it's just, I think the Java community is one of those communities that if you have problems with Java or some technical problems, there's always someone there to help you. There's always some code someone will loan to you, and it's just a great community. So that to me is like the biggest thing that I love about Java.
Thank you, Frank. Barry, what Java means to you?
6, and I've been writing Java books since 2000 with several editions for each book and lots of very small, admittedly small programming examples in each of the books. And with all those editions and all those examples, the total number of examples that have broken from one edition to the next is one tiny example. I can't say that about any other platform that I've written about, not even close. Thank you, Java. You've saved me tons and tons of work.
Thank you, Barry. Jean, your turn. What Java means to you?
Java was the language that let me grow from an entry-level developer to a speaker, an author, to make friends all over the world, to go to conferences and learn so much and have an amazing network. Thank you, Java, and happy birthday, Duke. Make a wish, and I hope that it comes true.
All right. Thank you, Jean. Chandra, my friend, what Java means to you?
Thank you, Sai. Thank you, Rodrigo. Java has been 25 years in the making, and when I first started, it was something I was just playing around with, and since then, it has become a language of my choice, my employment, and also my fun pastime. I am very grateful for the community that I'm in, and I've made a lot of friends, and I've attended a lot of conferences. So thank you very much, Java. Wish you a very happy birthday.
All right. Thank you, Chandra. Sai, what Java means to you?
Hi all. So Java meant my first job, thanks to Java. So starting from my first job since 2006 until now, I've been working on the Java stack. And thanks to NYJavaSIG, Frank, and all the friends here today, I've made great friends and gotten access to a great community. And as Jean said, amazing conferences. Yeah, Java has been a continuous learning experience for me and continues to be. So thankful to Java today. It's been amazing so far. Over to you, Rodrigo.
Thank you, Sai. So Simon, back to you. What Java means to you, Simon?
Yes, well, like Frank, I've I've been involved in Java not quite from the beginning. I joined Sun Microsystems in February 1996, originally as a Solaris engineer, and then I rapidly got into Java. So I've spent literally the last 20 years of my career talking about Java at conferences and events like this. And I have to say that in all that time, one of the things that I have enjoyed more than anything is Java user groups, because it's the idea that I get to go and talk to people, and I meet all these great people who are so enthusiastic about Java, and they're actually prepared to give up their free time to listen to me speak, which is quite something remarkable. So yes, happy birthday, Java. Hang on, where is it? The right way around. There we go.
Thank you, Simon. Dennis, what Java means to you?
In my case, I would say that this technology defined me as a professional, as a technologist, because generally speaking, I joined software engineering at my local university, but throughout the first years at the university, that domain was kind of boring for me. I was coding in C, C++, but still nothing could get me on the hook. But finally, when I learned from one of our professors that there is new exciting technology such as Java, I decided to spend one night and create the very first application using Swing and all the UI application. And after that, that looked to me really staggering, because I just created a really tiny application and could see how my application right now, visual buttons, etc., is up and running. And after that, just in a couple of months, I've got the very first contract and develop a Java application. In half a year from that time, I joined Sun Microsystems because I wanted to contribute to this technology. As Simon, I was kind of passionate about going and talking to the developers, presenting some technologies. And also, after Sun was acquired by Oracle, I joined the Java Micro Edition and Embedded team, kind of developing and adapting Java technology for mobile devices and embedded technologies. And right now, I'm still with Java. I love this technology. So thanks, Java, for defining me as an expert. So that's what I think about it.
Thank you. And I'll be the last one then. I think for me, Java is a little bit of what each one of you said here. Java helped me grow, helped me be a better developer. I learned a lot. And last year when I joined NYJavaSIG, Chandra opened the doors. Everybody welcomed me. I learned so much, and I learned about the power of the community. I think that's one of the best things that happened to me professionally. I learned how people help each other, how there's no ego. People like to see you grow. And I think that's the best part for me. Thank you. I think happy birthday, Java. Okay, thank you. Thank you, everyone. So now let's move to our talk tonight. I will ask you to use the chat on YouTube, use the chat to ask questions to our speakers. Our team is constantly monitoring the chat. So any questions you have, please use the chat. To start with, we would like to ask if you're a first timer here, if you have been here before with us, and also where are you from? We have people from all over the world in our previous events. So please let us know if you're first time and where you're from. All right. Once again, follow us on Twitter, YouTube. All right. Thank you very much. So let's go to our talk tonight. So our talk tonight will be about architecturing low latency Java system at massive scale. So we have two speakers tonight. The first speaker, Dennis Magda. He's the head of developer relations for Grid Gain System. You can find Dennis at conferences, workshops, and other events, sharing his knowledge about Apache Ignite, distributed systems, and building open source communities. Our second speaker tonight, Simon Ritter. He spoke at NYJavaSIG presidential events in last December, if I'm not wrong. He's a deputy CDO of Azul Systems and also a Java champion. He has twice been awarded a Java Rockstar status at Java 1 and currently represents Azul on the JCP Executive Committee and the Java SE Expert Group. In the name of NYJavaSIG Group, I would like to welcome both of you. Now it's a video.
Okay, thank you. Right, so let me share my screen. And I just thought I'd put this up because this was the thing that I found, which was the one of the first web pages for Java back in June 1995 with the coffee cup. Anyway, let's move on to the slideshow. Okay, so Dennis, do you want to say a little bit about the raffle?
Yeah, absolutely. So the folks, today we are going to raffle a couple of books, 3 books in particular. So take a risk. You just what you need to do is just to fill in this survey. In a minute, you will no longer see this slide, and the same slide appears once we get to the Q&A session of our talk. But in the same time, I do know that you can find the same link to the raffle in the chat window of your of the YouTube page. So find it there, and while you're enjoying this talk, take a risk, take a chance, and try to win one of these books. Thanks.
Okay, so yes, the title of the presentation: Architecting Low Latency Java Systems for Massive Scale. So I'm going to do the first part. I'm going to talk about what we do at Azul in terms of minimizing the latency associated with the JVM itself. And then Dennis will talk about the second part, about how GridGame can build on top of that in terms of delivering, again, low latency at massive scale. Right, so this is an interesting story. So this is about Southwest Airlines. And so it says 10 minutes that saved Southwest Airlines. And the reason for putting this up is because it demonstrates about the idea of being able to improve efficiency and actually save an airline by reducing latency. And what this is all about is because back in 1972, Southwest Airlines had all of 4 aircraft. And because they were going through some fairly tough times financially, they had to sell one of their aircraft in order to pay the bills and keep paying their staff and so on. And what was interesting about that was that rather than cutting the number of services that they were going to deliver, they said, no, we can actually continue to deliver the same number of services, same number of flights, using only 3 aircraft rather than 4. Now, clearly, the only way they could do that was by being more efficient. And so what they did was they reduced the latency associated with actually being on the ground. They got the time it took them to turn an aircraft around down to 10 minutes. So literally, the aircraft would land, pull up at the gate. It would take them 10 minutes to get all the baggage off, get all the passengers off, get all the passengers on, all the baggage that they needed back on, all the food, clean everything, 10 minutes. That was a really impressive thing, so that they could then manage to keep the same number of flights, but with only 3 rather than 4 aircraft. And so it's a sort of analogy in terms of what we're talking about in this presentation, which is the idea of being able to deliver the services that you want, potentially with less. And that's very sort of relevant today because, of course, lots of companies are having to look at how to reduce costs, but without delivering any less in terms of service. And in fact, often delivering more service, but with less resources. So that's the idea behind that particular story. Examples of low latency software. Dennis, do you want to say a little bit about this slide?
Yeah, so here is, that's a wonderful example related to the Southwest Airlines. But like today we are talking the technical stuff, right? And the solution, the architecture we are going to discuss with you folks is for software systems. And basically, if to talk about the low latency software systems, we can give you a couple of examples. First of all, everybody who is watching us today buys something from different merchants. And whenever you do a payment by swiping your credit card, behind the scenes, many issuing banks, acquiring banks, and credit card companies, they do verification of your credit card payments to ensure that there is that's not a fraudulent transaction, that this payment is allowed, that that's you who is doing the payment right now. And usually they have a small fraction of the time to complete, to perform thousands of verifications and to approve or decline your transaction. And usually this needs to happen within the boundaries of from 20 up to 200 milliseconds, depending on the bank or depending on a credit card company. Another interesting use case of the low latency systems is 5G-based solutions, telco companies who are migrating to that technology right now. With 5G, even if you check the requirements and the specifications of that protocol, the response time latency for the 5G networks is in the range of 1 up to 5 milliseconds. It means that most of the operations that will be fulfilled by those systems have to complete in that tiny time range. And finally, electronic trading, probably that's the most intense use case. Here is like whenever you are just watching the tickers of the market, whenever you're buying anything, the response time latency of different applications and systems that are used by traders lays in the boundary of like 20, like 100 nanoseconds, or microseconds, sorry, microseconds, even tougher. So like some of the examples of the real world low latency applications. So Simon, do you want to continue?
Okay. Yeah, okay. So one of the things that we find in Java is that, and I'll kind of get into this a little bit more in a moment, is about the fact that we have the JVM. And so we have a system that adds an extra layer in between our application and the operating system underneath. And some of what we do there is very powerful, and it allows us to do all sorts of things that saves us as developers time, it saves us effort, but it introduces things that make life more unpredictable for us, and specifically around the idea of garbage collection. So requirements for low latency Java-based stack. First thing is obviously that we want predictability. We want predictable, consistent latencies. So if you have something that you can actually rely on, and you can say, okay, I know when this is going to happen, I know what the maximum latency that's going to be involved is, then even if it's maybe slightly higher than you want, you can work around that. You can actually build that into your system and everything. But it's about being persistent. It's about being consistent. So what we want to do is make the garbage collection unnoticeable, because it's the garbage collection which is our biggest problem from the JVM's perspective. The simple fact that it is non-deterministic. We can't predict when it's going to happen. So what we need to do is make GC unnoticeable. Second one is lowest latencies, highest throughput. And Dennis, do you want to jump in here?
Yeah, in this case, as long as we want to try to assemble a Java-powered software stack for the low latency use cases, we want that stack to kind of to provide and to perform with the lowest latencies possible, and also to show the highest throughput. And with that in mind, generally, it means that it will be ideal if our Java-based systems can store data and process data right from the main memory. So if the main memory is your primary storage location from the for your application records. And I would say that the last requirement would be that, you know, many of the systems, many of the legacy systems that we have in the market right now, they are designed to be, you know, single node solutions, meaning that you might have some, you know, one physical machine or virtual machine, and whenever your workload or data volume grows, or you have to scale up your system. But the modern application systems that power 5G technologies or payments processing, the modern solutions, they want to switch to the horizontal scalability. And for us, it means that the task is to ensure that both application layer and our storage layer can scale out horizontally. So could you please, Simon, switch to the next slide? And our Azul Zing and Apache Ignite-based solution that we are going to dissect today is going to conform with all of those requirements. So first of all, we are going to explore how Apache Ignite in-memory computing platform can be used as a distributed storage layer that can keep data in memory, and also how we can use computational capabilities of that storage to perform various complex calculations, things like transactions, payments verification. At the same time, every cluster node you can see on this picture is a Java application. So basically, every individual Ignite node is no more than a Java process. And as Java process, it also can suffer from long stop develop pauses. And that's why with our experiment, with our use cases, we selected Azul Zing to see like what would be the difference, performance difference and the latency difference if our application puts some significant load to that cluster whenever that application starts executing transaction, and how the latency output and how the performance characteristics will vary with our cluster. So having said that, let's start diving into the details, and I'll let Simon to elaborate more on the capabilities of Azul Zing, why the technology is perfectly well suited for the low latency scenarios.
Okay, thank you. So yes, let's kind of dive into what we've done with Zing as an alternative in terms of a Java platform and a JVM. So the first thing we need to look at is what do we actually mean by speed in the Java world? And obviously, we can look at this from different perspectives. But one of the things that when I talk about what we do with Zing is kind of focusing on the idea of the JVM itself. And we're not talking about application speed. We're talking about what impact the JVM has on the performance of your application. So regardless of what you're doing in your application, how does the JVM impact on that? And I came up with a graph of the ideal performance for the JVM in terms of an application. And frankly, it's pretty straightforward. It simply says that what we want in an ideal world is for our JVM to start performing immediately at 100% of the possible level of performance it can give us. And our application will run, and that's all good. And we continue at 100% of our level of performance until we stop. I mean, it's not rocket science. It's very simple. Yes, that's what we want. However, the reality is somewhat different. If we look at a typical Java application, the kind of graph or shape of the graph that we see when we run our application is more like this. And this is a result of a number of different things that are happening within the JVM as it runs our application. So if we look at this in a little bit more detail, what we see is that when we start our application running, what's going to happen is the JVM is a virtual machine, Java virtual machine, JVM. And what it has to do is it has to load our class files, and our class files contain bytecodes. And bytecodes are the instructions for our virtual machine, but they're not the instructions necessarily that run on the machine that we've actually deployed it to. So whether it's an ARM processor, whether it's an Intel processor, then they have to be converted into those instructions. And that interpreting from bytecode to machine code takes time. And because the JVM does the same interpreting for every bytecode it sees every time it sees it, there's no real efficiency being gained there. So the machine runs very slowly. And if you go all the way back to the history of Java in the very beginning, 25 years ago, people often criticize Java as being very slow compared to C and C++ applications, because it was. And that was because bytecodes were being interpreted. To solve that problem, the developers of Java looked around and they said, okay, what can we do? And they came up with something that's been around for a while, which is just-in-time compilation. Now, just-in-time compilation says that when the application runs, we look at how many times a method is called, and we count that. And when a particular method gets to a certain level of being called a number of times, we say that's our hotspot in the code, hence the name of the JVM. When we find a hotspot, we say, let's compile that into native instructions so that we don't have to interpret the bytecodes every time. Now, in terms of our modern JVMs, the way that that works is it uses a compiler, a JIT compiler called C1. And C1 is designed to compile code very, very quickly. but it doesn't apply a lot of optimizations. So it's all about getting the code compiled quickly so we can run it and improve the efficiency. So we get a bit of an improvement in performance as we start to compile with C1. Now, the other thing that the code that's compiled with C1 does is it will also collect much more detailed profiling information about what the code is actually doing as it runs. We then continue to watch that piece of code, and as it gets used more and more, it's going to hit another threshold, and we'll say, okay, this is a really hot piece of code. We really need to recompile this. At that point, the code will be recompiled with a different JIT compiler. That's called C2. And the C2 JIT will recompile, but it will use the profiling information that was collected earlier to optimize that code as far as possible. And so we'll see a gradual increase in terms of our performance as more and more of our hotspots of code are compiled and recompiled into the optimum level of code. But what we do see, we see some significant dips in performance there, and those are down to de-optimizations. De-optimizations are a result of where the compiler makes certain assumptions about the way that the code works, and it uses speculative optimizations. Speculative optimizations are very good, but unfortunately, sometimes they don't always work out because you make an assumption that proves to be wrong. And so we have to throw away that code and then we have to recompile it. So we get a dip in performance as that has to be recompiled. So eventually we reach a steady state of optimized code, but then we've still got these dips in performance on a fairly regular basis. And that's as a result of garbage collection. So garbage collection happens. Pretty much all garbage collection algorithms will pause application threads in order to do their work safely if they need to move objects around within the heap. So this is the kind of graph that we're looking at. Now, what we're dealing with here is a managed runtime environment, and obviously there are two significant challenges involved there. The first of those is the garbage collector. And as I've already explained, it's the idea that the garbage collector is inherently non-deterministic. We can't predict when it will run. We can't predict how long it will run for. So that causes all sorts of problems in terms of latency. And the pause times associated with garbage collection can be quite big. In fact, they can be very big. And again, for most algorithms, the heap size dictates how long those pause times can be. The bigger the heap, the longer the pause times. And often people will try to minimize the heap in order to minimize pause times. Second thing we have to deal with is the fact that we're dealing with bytecodes, not machine codes. And so there's this warm-up time that's involved, and also the strategies that we use in terms of the adaptive compilation have a big impact on our performance. So what we did at Azul is we said, okay, how can we improve this? How can we, if you like, solve the problems that we're facing here? So we said, okay, let's not start from scratch. Let's take OpenJDK and the JVM, because it's a really good JVM, but let's try and change some bits of that to make sure that we can improve things like garbage collection. Now, the important thing is that once we've done that, we run all of the TCK tests on what we produce. And that's about 150,000 tests. You need to run them in order to verify what you've got conforms with the Java SE specification. And that's good because it means that what we're delivering is a drop-in replacement for other JVMs. You don't have to modify your code to use it. You don't have to recompile your code to use it. You can simply switch between JVMs, use the same class files, jar files, and everything will work in exactly the same way. Functionally, you just get better performance. What we do is we take all the garbage collectors that are available in Hotspot and we remove them and we replace them with a single one called C4. And I'll talk a little bit more about that as we go through. One of the things is that we only support this on Linux, and that's deliberate because we've also included some lower level features called Zing system tools, which are designed to improve the efficiency of how we can manage memory for the JVM at the mapping between physical pages and virtual pages. Second thing that we've done more recently is replace part of the JIT compilation system. So we've replaced the C2 JIT compiler with one that we call Falcon, and I'll talk a little bit more about that as well. And then the third thing is to try and eliminate this warm-up time that we see. We've introduced a thing called Ready Now. And again, that addresses the idea of minimizing how long it takes to warm up your application. just a couple of things about the Zing system tools. As I said, it's all about optimizing the way that memory management works, because if you look at Linux, it has a virtual memory system that maps between physical pages and the virtual pages and the address space of each process. That's very good. It's been around for a long time and it's been worked on, but it is designed for general purpose applications. Now, in the case of the JVM, that's a very specific type of application, especially from the point of view of how we use memory. So we allocate a lot of space for a heap, then we have to manipulate pages within that heap, and we have to move objects around, things like that. So what we said is, okay, let's use some lower level functionality, include a module in the kernel, which will allow us to handle the mapping between physical pages and the heap space directly. And then we can do all sorts of clever things in terms of cache coherency, contingency memory, and things like that. Since August last year, one of the things we found is that some of our customers said, well, hang on, if we want to deploy into containers, we don't really want to be interfering with the host operating system. We just want to put the JDK and the JVM into our container and then just ship it and not have to worry about anything. So now what we do is we don't install Zing system tools by default. We use some more modern system calls that are available in the Linux kernel, and therefore we can do that and not have to install additional software on the host operating system. If you want very large heaps, 1 terabyte and greater, then you do still need to use Zing system tools, but most microservices I would expect are not going to be in the 1 terabyte or greater range. If they are, you're probably doing something wrong with your architecture. So let's talk about C4. Now, C4 stands for the Continuous Concurrent Compacting Collector. And essentially that tells you exactly what it does. It's a collector which runs continuously. So it's running all the time your application runs. And most importantly, it does all of its work concurrently with application threads, meaning that we don't have to pause application threads in order to move objects around or mark safely whilst your application is doing its work. And secondly, even though we can do that concurrent thing, we can also compact the heap so that we can eliminate fragmentation. We can make sure that all the data is contiguous in memory and therefore optimize the way that the heap space is used and enable the collector to continue running without any problems. From a basic point of view, we take the same sort of approach that many other garbage collection algorithms take, which is that we use a generational heap. We take our heap and we divide it into 2 regions, young and old. The reason for that is that if you look at most Java code, all the objects, or virtually all the objects that you allocate, only exist for a very, very short space of time. And so if you can collect all of those objects in the young generation, you reduce the load on the old generation collector. Now, most algorithms use different algorithms for the young and the old. We use the same one, and it's more about making sure that we don't have issues of pauses by dividing the heap up in that way. So it's a better way of doing it, even though we're using the same algorithm. Very important thing about what we do with C4 is we do not have a stop the world compacting fallback position. Other algorithms like G1, like CMS, at some point will get to a stage where they say, we cannot keep up with fragmentation. We cannot keep up with the allocation rate. There isn't enough free space in the old generation. So we have to pause all the application threads and do a full compaction on the old generation. And that can take a long, long time, seconds, minutes, even hours. We simply do not do that. In terms of the algorithm that we use, 3 phases: mark, relocate, and remap. And all of those phases can be done in parallel. So that's important from the point of view of making sure that we can do those as efficiently as possible and do them as quickly as possible. How do we do this? Well, the key to this is what we call the loaded value barrier. And the loaded value barrier is effectively a read barrier, which means that every time you access an object from your application code, we will intercept that access and look at the object header to determine whether we need to do some work. So we test all of the object references, and that allows us to enforce 2 rules on what's happening with garbage collection. The first is that if we're in the marking phase, every object that you get a reference to in order to use it will be marked so that it's live data. So can't be accidentally garbage collected. The second thing is that if we're in the phase of relocation, that we will guarantee that the reference you get in terms of where that object is will be the correct one. So that if you make any changes to that object, those changes will not be lost because it's the wrong place and therefore the object has already been moved and we haven't updated the position. So you're guaranteed complete safe moving of objects whilst you're actually still doing your work. That allows us to do concurrent marking, concurrent relocation. Now, often people will say, well, hang on, if you're going to intercept every read to an object, isn't that going to degrade performance because you're doing extra work and there's a lot of object references, so that's going to have some impact? And the answer to that is, well, yes and no. The reason I say yes is because technically we do some work, but what we're doing is we're using bits in the object header and literally looking at those bits to say what is the state of the object and what is the phase of the garbage collector. And by doing effectively two instructions, which is a test on those bits, and then determining by that test whether we need to jump to a handler, most of the time we won't need to jump to the handler. So the overhead is simply to do the test and then not jump. If you look at that in terms of the underlying x86 architecture, that's a single clock cycle. It's a single micro operation. So we're talking somewhere in the region of 1 or less nanoseconds to actually execute that. So even though there might be a lot of object references, very, very small amount of time taken to do that. So the overall effect is negligible. And in fact, if you compare that to the amount of time it would take you to access data in the L2 cache, the L3 cache, or certainly main memory, it's far more significant the time it takes to do that than it is to do our test. How does this work? Well, when we start doing our marking phase, we, again, take a similar approach to other people, which is we say, okay, let's create a root set. And a root set is a list of all the objects that you have directly accessible from your application. We scan the stack, we look at the registers, we look at the static variables, and we build up a list of all the objects that you can see from those places. So that is clearly all the objects directly accessible. But many of those objects are likely to have references to other objects. And those objects will have references to other objects and so on. We need to build up a complete graph of all the objects that are referenceable from the application code. So our garbage collection threads will start working through the root set. And what they will do is they will look at the root set and say, okay, that object is still in use. We will mark it. We will set the bit in the object header so that we know that it's in use. The garbage collection threads will then start working through the following references to say, okay, that's got a reference to an object that's still in use, and that object's still in use, and that object's still in use. And we build up a complete graph by following all the links. Because the root set consists of independent objects, we can do that in parallel. So we can have multiple threads accessing the root set, dividing up the work and doing it more efficiently. Your application threads are still running. So at some point you may access an object and that object hasn't been marked. At that point, we're going to do our test and jump. So we'll test the bits and say, aha, this object has not been marked. We'll jump to a handler and the handler will set the bit in the object header to indicate that it's actually now valid data. So we guarantee that the reference you're going to get is an object that's been marked and can't be accidentally garbage collected. Now that means that effectively what we're doing is a very small amount of the garbage collection work in the context of the application thread. We then need to follow references from that object to trace the graph of referenceable objects. But we don't want to do that in the context of the application thread because technically it's an unbounded task. So to get around that problem, we simply hand that object to the garbage collection threads and say, make it part of the root set and follow the links from there. But obviously any application threads that access other objects will be marked. So that enforces our first rule. What we then need to do is a relocation phase. And we have objects spread out through the heap and we have fragmentation with gaps between them. We need to relocate the objects so that we can compact them. That's fairly straightforward because in this case, we've got 5 objects, A, B, C, D, E. To relocate them, we can move them to a different part of the heap and we can have A prime, B prime, and so on. So we've compacted our objects if we move them from one place to the other. So moving is effectively copying. We simply copy the data from one place to the other. To do that safely, we'll put a lock around it. So if you try and access an object whilst it's in the process of being copied, you will be blocked. But because most objects are very small and the speed of which we can copy an object is very small, the pause associated with that is going to be very, very small. So in the relocation phase, we can copy our objects around within the heap so we can compact them. We also create a side table, and the side table records the information about where objects have been moved to. So A has been moved to A prime, B has been moved to B prime, and so on. Having relocated our objects, we then come to the remapping phase. And in this phase, we have to update the object headers to reflect the fact that we now have objects in a new position. So our garbage collection threads will start work again, and they will use the side table, and they will say, okay, A has been moved to A prime. So at that point, they will update the reference in the object header, and they will set the bit in that object header to say, this object has been updated. So it's now valid. And obviously we can do that in parallel as well because we've got independent objects. Our application threads are running at the same time. So again, at some point we may access an object and our test on the bits indicates that this object has not been updated. So there's something that needs to be done. We jump to our handler, and the handler will then update the object header reference using the information from the side table, mark the bit to say that this has now been updated and correct, and give that reference to the application thread. So we guarantee, again, that you get the right reference for where the object actually is. And so there's no danger of losing the data or losing changes that you make when you use that object. What this leads to is what we call the pauseless collector. So essentially, there are no stop the world pauses in this. There are smallish, very small pauses where we have to do global safe points, but they're far smaller than any work that you would see in terms of other garbage collectors. This gives us a very consistent latency profile. And that's very important because it means that regardless of the heap size, you can go all the way from 512 megabytes up to 8 terabytes, and you won't see any increases in pause time associated with your application, regardless of how big the heap is. That's very different to other collectors. Similarly, regardless of allocation rate, you won't see changes in latency. You won't see changes based on how long the systems run for. You won't see any changes based on memory fragmentation or load profile. Very, very flat, very, very consistent. A little bit about GC tuning, because often what we find is that people will spend a lot of time trying to tune garbage collection to make it work the way that they want it to, and trying to eliminate these pauses as much as possible. And the reason for that is that there are lots and lots of command line flags that you can set in order to change the way the garbage collector works. Lots of garbage collection algorithms and then lots of flags for each algorithm. And these are two examples from real world situations where we've had customers that have set up their JVM to run a particular application. And I'm sure this is a familiar sight to many people in terms of all the flags that people have to use. I don't propose to go through all of these, but I will highlight one, which is that in both of these, they've set the survivor ratio to be a particular value. And that's a certain size part of the heap. So in one, they've set the survivor ratio to be 128. In the other, they've set the survivor ratio to be 2. And the question is, what's the right answer? And there is no easy way of saying, well, if you set it to 32, that will give you great performance for this application. Or if you set it to 256, it'll give you great performance for a different application. So you end up with very much trial and error. And the problem with that is that that's only one parameter. So you've got one parameter you can fiddle around with and try changing it to different values and seeing what effect it has. But there are lots and lots of other ones. So you end up with an n-dimensional space, and it's very difficult to come up with a simple set of values that give you good performance. If you look at Zing, the equivalent set of performance tuning is just this. All we do is we set the heap size, and that's it. There is nothing else to do. You set the heap size and off you go. And so long as you've got enough heap size to keep your application running without running out of heap by allocating too many objects, then that's all you have to do. And typically what we do in terms of tuning is just to say, okay, well, set it nice and big, make sure your application runs quite happily, and then just basically tune it down. So reduce the amount of heap space until you kind of get to the point where you're starting to run out of space, and then move up a bit, give yourself a bit of headroom, and then you've got a tuned system. Admittedly, there are a couple of other flags that we can use, but that's really for when we're trying to really reduce the latency even further. So how can I show you that this actually works? What we've done is to produce a little open source tool called JHiccup. And the idea of JHiccup is to record the latency that's associated only with the JVM and everything below that. So JVM, operating system, hardware, and everything like that. So it's not looking at the latency of your application, how long it takes you to process a transaction. It's how long does the JVM impose latency on your application. To do that, all we do is we add an extra thread alongside your application. And to avoid the problems of Heisenberg's uncertainty principle, the act of observing something changes what you're observing, we don't really do very much in that thread. All we do is spend most of our time asleep. So we go to sleep for 1 millisecond. When we wake up, we look at the system clock and we say, we expected to wake up 1 millisecond later. What time did we actually wake up? We can use nanosecond resolution, so we can do that very accurately. Clearly, if you're running on hotspot and a garbage collection pause kicks in, maybe it's 20 milliseconds, then when we wake up, we'll be 20 milliseconds later than we expected to. We can record that information, generate a nice histogram log file, and then graph that information to show what was actually going on. Here's an example. This is Elasticsearch running on a 128 gigabyte heap. And in this case, on the left-hand side, we've got a hotspot. What we see here is a very typical hotspot GC graph. Lots of small spikes indicating minor GC pauses. The young generation's filled up, has to be collected, and we move stuff into the old generation or the survivor spaces. And then we've got two big spikes, and those indicate major GC pauses, where we've had to do some work on the old generation, longer than the GC pauses for the minor GC. If we look at the right-hand side and we look at Zing, it's much more random. It's much more difficult to predict what's going on there. And you might say, well, hang on, if high is bad, higher the graph, then the worse things are, then your graph of Zing doesn't look very impressive because it's all over the place and there's big spikes there, and it's no, I'm not impressed by this at all. But I have deliberately misled you. So I've actually scaled the graphs differently. On the left, the hotspot graph is from 0 to 8 seconds, so 8,000 milliseconds, meaning that most of our minor GC pauses are around half a second, and the longer major GC pauses are about 5.5, 6.5 seconds. On the Zing one, I've scaled it from 0 to 80 milliseconds, indicating that what we're seeing here is mostly in the range of 10 milliseconds, a couple of spikes in the sort of 40, 50 millisecond range. If I scale the graphs the same, then we see the effect very clearly that Zing just eliminates all of the latency associated with garbage collection. It just disappears completely. So just want to talk a little bit for a couple of minutes about the Falcon JIT compiler, because one of the things that is an issue here is people say, well, hang on, okay, garbage collection reduces latency, but the effect of that surely is that because we're dividing up the garbage collection work whilst the application threads are running, aren't we going to see a drop in throughput for our application? Because we're taking some of our threads and using it for garbage collection, reducing the number of threads that we can run for our application. Aha, well, we thought about that. So we looked at the way that the JIT compiler works, and we said, okay, if you look at C2, it's about 20 plus years old. And the way that it's been designed, it's just like a big ball of string. And so what we needed was an alternative that was easier to maintain, easier to enhance and add new features to. When we looked around, we found there was a very nice open source project that had been around for a while called LLVM. It's really about the sort of back end of a compiler, takes intermediate representation and generates heavily optimized code. Primarily designed for languages like C and C++, but there's other ones like Swift and so on. And it's supported by a lot of big companies like Intel, NVIDIA, Microsoft, Apple, and so on, all of whom know a lot about how to write compilers for particular chip architectures. So what we did is we said, okay, let's take that and use it as a replacement for C2. We will generate intermediate representation that can be passed into that from the JVM. We'll integrate it with the garbage collector and so on, and get code out of the back of it. What that gives us is much better performance in terms of speculative optimizations, much better intrinsics, more inlining, and so on. So if we look at just an example of that, if I take a piece of code like this, it's a very simple loop where I'm taking an array and I'm adding up the contents of that array. Give that to any modern compiler and it will say, aha, we can use vector operations for that. Vector operations are just wide registers that you can load up multiple elements from your array into and then apply a single operation to them in a clock cycle. So it's single instruction, multiple data. So in that case, no problem, everybody can do the same thing. If we make the situation a little bit more complicated, we introduce a conditional statement here. So we're saying that we want to only add the elements of a second array to a first array if if the second one is even, then modern compilers struggle with that. They won't look at that and be able to identify it as something that can have vector operations applied to it. Remember, this is just one example of what we can do with Falcon. And if we look at the code that's generated by the JIT, this is C2. Don't worry about all the details of this and the actual individual instructions. But what the red boxes identify is the fact that for this loop, C2, all it's done in terms of optimizing is loop unrolling. And it's only loop unrolled for 2 elements per iteration of the loop, which is not really that impressive. It's just doing, okay, let's do 2 elements per iteration of the loop. That's it. If we look at Falcon code, it looks more complicated. There's more code involved here. But what's happening is we're getting much better optimizations. Falcon has identified that we can use vector operations on that. So it has done that. And on this particular machine, we've got an AVX2 instruction. So it's a 256-bit wide register. And we're then also able, in this case, to do loop unrolling with 4 elements per iteration. The overall effect is that rather than doing 2 elements per iteration of the loop, which we did with Hotspot and C2, we actually get 32 elements per iteration, many of which are done in parallel. So it's even better for the Falcon JIT compiled code. So we get better performance overall, which eliminates the effect of the garbage collection happening in parallel with our application. Last thing to talk about is ready now, and the idea that we have this warm-up time associated with having to do all the compilation and the latency that's involved in doing that and reducing the performance of our system. So we have this application warm-up, and the problem is that every time you start the same application, it does the same thing. So it has to go through the same process of interpreting C1 compiled code, running the profiler, generating all the code and de-optimizing and so on. What we've done is to introduce ready now. And the idea here is that you run your application for a while, get it so it's warmed up, and then you record a profile. And that profile includes 4 pieces of information. All the classes that currently loaded, all the classes that currently initialized, all the profiling data that was generated by the C1 compiled code, and most importantly, any speculative optimizations that failed and resulted in a de-optimization. So we made the wrong assumption, had to throw away that code. What we can then do is take that profile at any time. We could take it after 2 minutes, we could take it after 2 hours, we could take it after 2 weeks, whenever you're happy with the performance of your application. We can then use that for a future run of the application. When we start the application the next time, what we do is before we get to the main entry point, we will load all the classes we can, initialize all the classes we can, and then take all the methods that were compiled previously, pass them to the JIT compiler with the profiling information and the speculative optimizations that failed, and compile the code based on that. So that by the time you get to the main entry point, you're literally going to be running at about 98% of the performance you had when the profile was taken. Couple of transactions just to kind of kick everything into gear, and you're back and running at the full speed that you had when you took your profile. This is really good. Now, Without ready now, the overall shape of our graph is like this. So we have a slope which shows that it takes time to warm up. The drawback, if you like, with ready now at first glance is this, because we have to do a whole lot of work before we get to the main entry point. So there's this class loading, initialization, and compiling, and that takes time. So there's effectively like a dead spot before the application actually gets going. Now, even though the graph is much steeper at that point, the overall effect could be not quite what you're looking for. So in that case, what we've done is to improve things even further. So now we have what's called compile stashing. And compile stashing says, okay, let's take our ready now profile, but let's also record all of the code that was compiled during that run of the application. One of the things that we know is that the Falcon JIT compiler is fully deterministic. What that means is that if you take the same method, you haven't recompiled it and changed it, take the same method, provide the same profiling parameters, then what you're going to get from the JIT compiler is the same compiled code. So that means that provided we can prove that we have the same method to start with and the same profiling parameters, then we don't have to recompile it. All we have to do is take it out of our cache and reuse it. Avoids a lot of the compilation at JVM startup time. So now we go from the idea of, okay, having this blank spot at the beginning without compile stashing, and now what we can do is reduce that blank spot by up to 80% and reduce the CPU load by up to 60%. So we're actually getting very, very close to that perfect graph now. So just to summarize this part of the presentation around Zing, what we're doing is we're saying, okay, let's take that graph in terms of latency, in terms of performance, and use C4 as our garbage collector to eliminate the problems of the dips in performance and the latency there. Let's use Falcon to raise the level of performance so that we're not hit by the fact that the garbage collection is happening parallel with our application code, and use ready now to push our graph out so that we can eliminate a lot of this warm-up phase. So what we say with Zing is start fast, go faster, stay fast. Consistent latency, consistent throughput. And that happens regardless of the load you've got on your system. Very important, as I've said already, simple replacement for other JVMs, no recompilation, no recoding, simply switch to using Zing and off you go. And you can try it free for 30 days, azul.com/Zing trial. So that's the end of my part of the presentation. Now I'm going to hand over to Dennis, who's going to talk about the Apache Ignite and the use of Zing. So let's see if I can
wonderful.
Sharing.
Thanks, Simon. Folks, give me a second.
Sure.
I'll switch to my desktop. I'll be sharing and drive the presentation. All right. That's the button. We are sharing. And Simon, could you do me a favor confirming that you see the slide?
I can, yes.
All right, wonderful. Okay, what we are going to explore next? With the next section, we want to show you folks a real case study, a real use case of a low latency system, and some of the benchmarking results done for that solution. And for that benchmarking, for that benchmark, we selected Apache Ignite. You will understand why, and Zing virtual machine. And now I think it's already obvious why Zing is one of the best fits for the low latency use cases. So, like, what are the details of that payments benchmark? So, generally speaking, the architecture looks as follows. We deployed 3 nodes grid gain or Apache Ignite cluster. It doesn't matter. And that cluster was deployed in Amazon. We selected the following machines of this configuration. Overall, we had the system had 72 cores cluster-wide, and the capacity, the memory capacity cluster-wide was 600 gigabytes, and we had 45 terabytes of data on disk. The application itself that was connected to this cluster was performing several different benchmarking tests. First of all, we were comparing how the tests perform for Azul Zing virtual machine in comparison to OpenJDK hotspot solution. And the scenarios are as follows. First of all, we loaded 200 gigabytes of application records in memory on those 3 cluster nodes. No any persistence at all. The second test, we performed the same test, but right now the system again was caching all the data in memory, but also at the same time, the same copy of the data was located on disk, on the same cluster nodes. And finally, if you remember our opening slide when Simon was presenting the use case of Southwest Airlines, how the airline could reduce their costs by selling one of the aircrafts, by still they're able to perform and do to perform the same number of flights on the same routes. We are going to preload much more data to this cluster, like we are going to triple the size, but we are not going to scale out our cluster, even though it is possible. And the application is simple. Actually, the application is performs the real test that is done by one of the well-known banks, and that bank uses this test to validate different technologies for payments processing, for validation of different payments scenarios. And whenever we are going to talk about every individual single transaction that the application is going to execute in the cluster, every single transaction is going to access up to 20 records of the data stored in memory or on disk. Also, when you're going to see the results for transactional reads. Transactional means that the system has to perform up to 1,000 reads per second. And the target latency is has to stay within the boundary of 50 milliseconds for 4/9 percentile. Pretty tough scenario, especially for Java, considering garbage collectors. And when it comes to the transactional updates, the throughput rate is higher, so we need to be able to perform 2,000 operations per second. But the target latency is lower. We are allowed to complete every operation within the boundary of 50 milliseconds. And that's again for 9th percentile. Only one remark that is related to the transactional updates. When we are talking about updates, you have your distributed in-memory cluster. And when you are updating any record, like my bank account record, then a copy of the record will be updated on the primary copy of the record will be updated that is stored on one of the cluster machines. And also the backup copy of the same record will be updated on some other machine. And generally, here is Ignite uses special two-phase commit protocol executing its distributed transactions. And as you remember, Simon was already referring to JHiccup. That tool was used to measure the performance results. We also use micrometer to measure the latency differences. And finally, the graphs you're going to see, we were executing all the tests throughout the 2 hours time span. So now let's, before kind of walking you through the details of Apache Ignite and how Apache Ignite was used, how Apache Ignite used Azul Zing for the architecture, let us show you first results. Considering this use case, we preloaded just 200 gigabytes, almost nothing to our cluster. And these are the results for the transactional reads. To the left, you can see the graphs of the hotspot environment. That's when every Ignite cluster node was running on a hotspot virtual machine. And to the right, you have the same results, but for Zing. And as with Simon's graphics, it might look like the results are relatively similar, but in fact, once we equalize our scale, we can see that with hotspot, we were not able to meet the criteria of completing all the operations within 50 milliseconds. While with Azul Zing, it was possible. With Azul Zing, like 100% of the operations, like 100% percentile, everything met the requirement. When it comes to the transactional updates, again, let's compare the graphics. So again, if we equalize the scale, that's the difference. With Azul Zing, the numbers are perfect, no any worries or concerns. But with hotspot, we had some spikes. But still, when it comes to writes, we determined that hotspot behaves much better if to compare to the read operations. So before continue and showing you the rest of the graphs, right now let's do so-called speed dating with Apache Ignite, so that you have a better understanding of what are the capabilities of that platform and what are the primary use cases, and why Ignite together with Azul Zing is a pretty decent solution for low latency architectures. So first of all, if to do this breakdown, those of you who are familiar with Apache Ignite already, you most likely have already seen this graph. Ignite is a platform. It's like your Lego constructor. It comprises of many different building blocks. But when I usually try to explain it in simple words, for me, Ignite includes two primary components. The first one is it's truly distributed multi-tier storage. And the second component is a variety of APIs that are integrated with this storage. So speaking about the storage, by definition, as a in-memory computing platform, Ignite is capable of storing all your data set, all your indexes, and serve your requests straight from main memory. At the same time, keeping a copy of data in memory is not enough, to take Ignite. It would be not enough to take Ignite into any real production and use it for a real production application. That's why when it comes to the disk tier, here you have two options. Ignite can persist all the changes in external databases like Oracle, MySQL, or like Postgres, or you can enable Ignite all native persistence. And after that, Ignite will keep a copy of your records, not only in memory, but also on your flash drives, on your Intel Optane drives, etc. And on top of this storage architecture, Ignite provides APIs that are that most of you are familiar with. For instance, you can use SQL queries to process and request and read data back to your applications. You can run key value operations. You can do transactions. You can create your custom Java tasks and get them executed using compute grid APIs. Like some of these APIs we are going to check today, and you will understand better how those APIs are used for the payments processing scenarios. So everything you see in the middle is available in open source. It belongs to Ignite, it belongs to the Apache Software Foundation, and to the left, to the right, in blue blocks, those are enterprise features that are provided by GridGain. GridGain is one of the major contributors to the Apache Software Foundation and to Apache Ignite. And like most of the features are in open source, but also if you need things like management and monitoring, backups, advanced security, like point-in-time recovery, you can get that with GridGain. So those are features, but right now let's talk about use cases. As a platform, I can define three primary use cases Ignite is selected for: as a cache, as a database, and as a component of your digital integration hub architecture. Let's quickly review all of them. Ignite is a cache. So the story here is pretty simple. I do believe that most of you who are watching us right now on the line are familiar with various distributed caching technologies. You might already use Redis or Hazelcast or Memcached, or like there is a myriad of different platforms that provide distributed caching capabilities. And Ignite is not an exception here. You can take Ignite and deploy it as a distributed in-memory cache on top of your databases, or just you can cache some of the applications. But then the question arises, what's the difference? Like, why would I select, let's say, Ignite, and why can't I just take Redis? So I would say that in most of the use cases, for the simplest use cases, if you just need some basic caching, then most likely you will select Redis, unless you need SQL, unless you need transactions, or unless you need, let's say, unless you want to execute your Java tasks on your cluster nodes in the MapReduce fashion. If you need those capabilities, then Ignite is a caching solution of your choice. Ignite provides standard SQL, transactions, compute, and many more. The other use case is for greenfield applications, so like those applications that we are designing these days and building from the ground up. In that case, I personally see that people prefer to use Ignite native persistence as a disk tier, only because so that we can simplify the overall architecture. The fewer components we have, the simpler it would be to support and maintain our system in production. And here is, but what's the primary difference between, let's say, Ignite native persistence as your disk tier versus, let's say, Oracle or MySQL database that also can cache data, that can also persist records cached in Ignite. So with Ignite native persistence, I would say you're getting two primary benefits in return. First of all, you don't need to cache all the data in memory, because Ignite native persistence, every node you can see on this picture will keep a copy of a record on disk, meaning that depending on your memory capacity, you can cache 100% of the data in RAM, or you can cache a subset of the data. And the other benefit is the startup time of your cluster, the startup time of your applications. As you remember, Simon was introducing us to the Ready Now technology that takes the profile of your application and then can use that profile to speed up the bootstrap of your application the next time you're going to launch it. And with the native persistence in mind, you're getting the same capability of it. As long as all the data is always stored on disk, and if by any reason, for any reason, your cluster went down, once the cluster is restarted, Ignite is up and running, it becomes operational. Your applications can send all the requests to this cluster, and Ignite will be serving all the data from disk. And the memory tier will be warmed up in background. So that's what you're getting, like much faster startup times. And the final use case of Ignite is a component of digital integration hub architecture. That's one of their architecture, you know, like many of us, especially those who work for big companies, we know that there are different data silos. Like there are many databases. Some of the databases are used for service A. The other databases are used for other set of applications. But sometimes there is a group of services on applications that we use internally or sell to our customers that need to access several databases of our system. And that complicates, you know, the architecture. We need to develop different microservices. We need to develop some shared APIs, etc. And Ignite here can be presented as your shared distributed storage in memory plus disk. It can keep data, store data from various disjointed databases. And all your APIs can work with Ignite as a one single shared layer. You should not, most likely you will not have a shortage of different capabilities in terms of how you can access your data, as long as Ignite, you've seen, if you remember the first slide, SQL, like key value transactions, that's like, those are primary APIs. We usually need to do something with our records. So right now, what's the relation with Zing, and why like those benchmarks that I showed you before show, let's say, show that the results with Azul Zing are much better than the performance and latency results of the hotspot-based solution. So I would like to talk about Ignite memory internals. Ignite, if to take a single node of our Ignite cluster, again, Ignite node is just a Java process, it's just JVM instance. But when it comes to the data storage layer, Ignite stores all the application records in an off-heap memory space. So if you remember during, like Simon was talking how Azul Zing can detect, like, can kind of use various optimizations because the virtual machine knows the internals of the physical mapping, the mapping of pages from physical space, like from virtual space to the physical space. And when it comes to Ignite, we actually borrowed that idea of the operating systems. And when it comes to Ignite's off-heap memory, all the memory space is split into pages of the fixed size. And inside of those pages, we store your application records. So like your application records and data records. But it's inevitable that as a Java middleware, Ignite is going to utilize Java heap. So when Ignite node, your cluster node, is going to use heap, it's obvious. Your application is going to issue commands to this cluster node. You're going to execute SQL queries on that node. And all those operations are going to copy some of the records from the off-heap space. They will bring them to Java heap space, while the node will be creating a result set for your application. Also, your custom Java code that can be executed on this cluster machine can generate some temporary objects. And overall, when it comes to the low latency use cases, what we see is that as long as the throughput of those use cases is high, like even with this typical benchmark, the system needs to process 2,000 updates and 1,000 reads per second. That Java heap generation, like objects generation rate in Java heap will be intense. And that's why we need a virtual machine powerful enough that can minimize the garbage collection process and do other various optimizations like those that can be done with the Falcon. And when it comes to the scalability question, let's say that it's all simple. With Ignite, you see that your workload grows, or you are about to store 2 times or 3 times more data. Just go ahead and scale out your cluster. That's just one extra command that needs to be issued by your IT administrator, and you're good to go. Your cluster is scaled. So when it comes to the persistence, and let me elaborate a bit more on Ignite native storage. So Ignite is designed to work well with both tiers, with memory or with disk. Its performance characteristics will be superior if you are capable of keeping all the records in memory. But also, let's be serious. Nobody will take cache in production if there is no any copy of data on disk. And that's why if you enable Ignite native persistence, what happens is that every individual cluster node will start keeping a copy of your records on disk. And by default, not by default, like all the times when you do this, 100% of the records will be located on disk. And then you can decide how much of data should be cached in memory. So what happens in terms of the records consistency? What you see on the diagram to the right, let's assume that our application issues an update. This update arrives to our cluster node. First of all, this cluster node will update the in-memory copy of the requested record. And after that, immediately, it will write down this change to the local write-ahead log file of this node. And as the third step, this cluster node will acknowledge that this update was processed, and it will let your application to carry on with the rest of the instructions it has. And then over the time, at some point, this cluster node will trigger so-called checkpointing process. What the checkpointing does, it takes and dumps all the dirty pages from memory to the partition files. Dirty pages are those pages that were updated in memory, and but they will not updated on disk in partition files. The changes were written to the write-ahead log files, but still we want to write down those updates to the partition files that store the final actual copy of our record. Why do we do this? First of all, that will help us to trim the size of the log files. We don't want, and also it will let you to read data straight from the partition files if any record is not available in memory. All right. So having said that, right now, let's see what would be the difference in terms of the performance if we decide to enable native persistence for our cluster, but still we are going to store the same amount of records, like 200 gigabytes cluster-wide. So, and that's the graph. Again, those are transactional reads, but right now with Ignite native persistence. To remind you, to the left of the screen, we have the graph of the hotspot. That's when Ignite cluster nodes were running on hotspot machine, and we use G1 for garbage collection. And to the right, sorry, to the left, yes, we have J1. To the right, we have Azul Zing C4. So that's the graph. But again, we misled you here. And in fact, if we equalize the scale, those would be the real numbers. So as you can see, with a hotspot, we were not able to meet the target latency anyhow. The target latency, to remind you, was 15 milliseconds for 9 percentiles. While with Azul Zing, no any troubles. We were good to go. We enabled this persistence, and right now, in addition to the memory copy, we have the same copy on disk. How about updates? Because with updates, the things are getting really complicated, because right now, whenever any transactional update arrives to our cluster node, we need first to update the memory copy, then we need to write the write-ahead log files of every cluster node, then we need to update the backup copy of the records. And that can truly, stress out our throughput and latency characteristics. But again, so by looking at this chart, you can think that the numbers are the same. But if you equalize the scale, you can see that with hotspot, unfortunately, we were not able to meet that target latency, even for, like, I would say that we could meet it only for the 19th percentile, but that's not acceptable for payments benchmarks. Like, nobody would take this in production. But with Azul Zing, it's all right. We are good to go. And final test that we also usually do for low latency scenarios is, let's try to stress out our system. If you remember that story about Southwest, let's try to do the same with Grip Game. We tripled the size of the data. So instead of storing 200 gigabytes right now, let's store 600. But I don't want to scale out my cluster. Yes, I can always, like, whenever I double or triple the size, I can add extra cluster nodes of Ignite. But let's see what are the capabilities, what's the borderline of our system. And to do that, we cached only 30% of the data in memory, meaning that for most of the queries, especially for reads, Ignite will serve all the data from disk because the records will not be available in memory. And those are the graphs. I would say that here's finally we were able to kind of swell the momentum of Azul Zing, because finally we could see something, scary and notorious. But in fact, again, if we equalize these graphs, you can see that with hotspot, again, no way we can meet those latency requirements. But with Azul Zing, at least, we still are in the range of that latency for the 49th percentile. And only for the 100% operations, we can see that some of the operations did not fall in that range of 50 milliseconds. But that's like 100% of the operations. Nobody was asking us to do this for 100%. When it comes to the updates, pretty similar graphics. Let's equalize the scale, and you can see that, again, with hotspot, unfortunately, not the way to go for us, while with Azul Zing, only for 100% of the operations. Some of the operations, if we are considering hundreds of them, fail to meet the percentile. But for 9s, we are good. And finally, guys, so let me kind of present you the architecture, like how credit card payments verification happens. So let's assume that, and let's take the mainframe way. So basically, I had a I was involved in some of the projects. And I would say that still mainframes are widespread, and many mainframes are used by banks and credit card companies and by insurance companies, etc. And the mainframe is an excellent solution if you'd like to reliably and consistently process, credit card payments. Because usually what happens, let's say that I went to Starbucks, to nearest Starbucks, and right now I want to pay out a cup of coffee. What happens next? I know that that mainframe will keep the transaction history of my bank account. For instance, all the latest purchases I fulfilled through that credit card. Also, there will be a separate file on disk that keeps the transaction history of Simon's payments. And when this system will be verifying your transaction, approving or declining it, it will be running various verifications. On average, the credit card companies or banks, they validate like thousands of different variables before they can accept or reject your payment. And for that, they also, one of the basic checks for sure, they will check last 100 of your payments to ensure that you're paying from some location where you live, so that nobody has stolen your credit card information. Also, they will be using Starbucks transaction history for some of the variables verification. And Starbucks history is massive. But with mainframes, the solution performs extremely fast because all the transaction history for merchants like Starbucks or for individual payers like my account or Simon's account, all the transaction history is stored sequentially. So whenever any payment request arrives to a mainframe, the mainframe will be able to quickly open that file. And at the very top of that file, it will have details about the last transaction. And then it can drop down to the analyze, let's say, hundreds or thousands of the latest transaction, and it will be calculating thousands of different variables to verify whether your payment is fraudulent or not. So how do we tackle these kind of scenarios with distributed systems such as Apache Ignite? First of all, we need to understand how Apache Ignite stores data. Let's assume that we have accounts table in Ignite. And those accounts table, as with mainframe, it will keep information about my bank account, like about Simon's account. And our details about our bank accounts can be stored on different cluster nodes. But when it comes to the purchases, to the transactions, to our real purchases, let's say all the Simon's account, Ignite can keep them on the same cluster machine. It's so-called affinity-based collocation technique. So when the related data is stored on the same cluster machine. And that's what happened here. The SP stands for Simon purchase. So we have Simon purchase 1, 2, and 3, and 4. And all my purchases will be located and stored together on the machine, on the node that keeps my bank account. So that's one optimization. That's like one of the basic techniques that is adopted by every distributed system. Let it be a distributed database, let it be a distributed cache. Most likely with any system, you will be able to keep the data in this collocated fashion. Next task. When I was talking about the credit card payments verification process, you have to process and you have to calculate thousands of variables to ensure that your transaction is not fraudulent. And if you're going to, with mainframe, the things are simple. Mainframe just receives the request and then it can run many calculations, and all the calculations are local. The data is available locally. With the distributed systems, such as Apache Ignite, the things are complicated. You cannot just, barely ask your application to go to the cluster and read the history of my latest 1,000 payments, or the history of the latest transactions at Starbucks, because you will be moving massive amounts of data over the network from the cluster to the application. It will be a huge overkill. That's why distributed systems such as Apache Ignite allow us to execute compute-intensive or data-intensive logic on the cluster nodes that store actual data records. And Ignite goes with so-called compute grid, compute APIs. That's just an implementation of the MapReduce framework. So with MapReduce framework, we know that we need to do two things. First, we need to create our task, and then we need to execute this task. And once this task is scheduled for the execution, it will be sent over to the cluster nodes. That's the step 2 on this diagram. And the cluster nodes will be running this logic over the local data set, and no data will be moved over the network. And finally, when every node completes its part of the execution, it will respond to your applications, probably sending some result set, and the application will have its chance to reduce that result set and return to the rest of your business logic. So right now, keeping that in mind, affinity collocation approach, and that you can also run your Java tasks on the cluster node, let's try to see how that system can look like based on Apache Ignite or like on similar technologies. Again, I'm going to the nearest Starbucks and I want to pay. And what happens right now with my 3 nodes cluster, my transaction history, all my transactions, will be stored on one of the nodes. And the same is true for the payments done by Simon. And that's good, right? But when it comes to the transactions history of merchants such as Starbucks or Amazon or Walmart, whatever, it's just impossible to keep them on a single cluster node, because otherwise every cluster node should be running on a mainframe. So what's the purpose then? But with distributed systems, we can architect the data distribution in such a way that one of the cluster nodes will be storing the first chunk of Starbucks transaction history, let's say the first 10,000 transactions, while the other node will be keeping like the rest transactions. And then you can proceed with the same approach if whenever the transaction history of Starbucks grows. And right now, like whenever I'm going to swipe my credit card, this transaction will arrive to the node that stores my bank account, that stores the transaction history of my payments. And then that node will start checking my transaction history and also some of the variables that verify whether my transaction is fraudulent or not. They would need to access the history of transactions performed at Starbucks, not only my transactions, but someone else. And that's why this node will send a request to the other node, asking it to iterate through the second chunk of the Starbucks transaction history and to help to calculate different performance, like fraud detection variables. And that helps us to utilize all the resources of our cluster to calculate, to do the same task that we can do with mainframes. But right now, we can scale it out. All right, so as a summary, what we discover, low latency systems, they are extremely picky about latency. Usually those systems run high through, they can be characterized as high throughput systems. They perform thousands and thousands of various operations per second, but also they do care about the latency. And usually they talk in the terms of like 4 nines or 2 nines percentiles. So that's why whenever you are building a low latency system, you need to eliminate the possibility that a garbage collector will diminish, like will affect your latency characteristics. That's why Azul, what we discovered, and that's what we are doing right now, whenever we Ignite is selected for any low latency systems, we are going together with Azul Zing virtual machine as a complete software stack. Also, when it comes to the, let's say, the second requirement, we want to get the lowest latencies possible and high throughput. You can store the data in memory and you can execute your logic in memory. That's why Azul can take care of your Java heap records. So those low latency system will certainly stress out your Java heap, and you will have a lot of garbage collector cycles. That's why we want Azul to take care of that. But when it comes to some permanent storage that can keep our application records in memory, that's what you can select Apache Ignite for. And finally, horizontal scalability. If you are going to triple, like or quadruple your data size, you can always scale out linearly Apache Ignite. With today's presentation, we decided to reuse the same resources that were given to our system. That's why whenever we tripled the data size in Ignite, we decided not to scale out the cluster, but rather, serve most of the records from this. But anyway, if you need to scale out, you always can scale out. And finally, I think that's we're about to move to the Q&A session. And here is that slide. You can find some of the useful links. So if you want to learn more about Azul, go to the main website, and the same is true about Apache Ignite. So let us switch to the Q&A. And Simon, do you have any closing words?
Okay, perfect. Thank you. Thank you, Dennis. Thank you, Simon. It was a great presentation. So there was a lot of questions in the chat. Simon, I don't know if he answered all the questions already, but he was really good on it.
But we're going to ask them anyway for people who are watching this on video later and have not been monitoring the chat.
I agree.
So some of them may be easy since Simon's had the chance to think about them. And I've tried to group them by topic rather than linearity. So the first question has 3 parts. What is MTS? How often is an MTS release? And does Zing support MTS?
Right, so MTS is medium-term support, which is what we came up with as an addition to long-term support. It is not supported on Zing. So for Zing versions, we're only doing the same as the long-term support versions for OpenJDK, meaning that we have a Zing JDK 8, we have a Zing JDK 11, and the next one will be Zing JDK 17. That doesn't seem to be a problem for most of our customers because they're looking for long-term, they don't want to move very quickly because the typical places where they deploy Zing are into the kinds of environments where they're not looking to replace the JDK or the JVM on a regular basis. In terms of medium-term support, the idea is to allow 2 versions between long-term support to be used with extended updates. So this is for Zulu, the build of OpenJDK. Right now, we are doing medium-term support for JDK 13, and we will also do medium-term support for JDK 15. And we will continue to provide updates for both of those until 18 months after JDK 17 comes out. So you could then move to 17, and you've got 18 months to do that because we'll continue to do updates. So that's the idea behind medium-term support.
Thank you. My favorite question that you managed to not answer, because it was early on when you were talking, was someone asked about they've done some custom work with OpenJDK and learned that keeping the code updated and updating security patches is a pain. How do you deal with that for Zing?
Yeah, I mean, it's obviously, it's more work for us. A lot of security patches we can do as part of our backporting work anyway. So, we're part of the vulnerability group in OpenJDK, so we're already helping to develop these patches anyway. But obviously, when it comes to certain aspects of Zing, where it's things that we've changed, so C4 or for Falcon, then we have to be a bit more aware of how security vulnerabilities affect us, so we may have to do more work. Obviously, we pick up any security patches from LLVM directly, so if they have things that they've addressed, then we'll pick those up and bring those in. On the C4 side of things, we obviously keep a careful eye on that. But yeah, it's obviously a lot of work. We have quite a large team of engineers. I think Azul, we've probably got something like 80 to 90 engineers in our organization. So we do spend a lot of time doing this kind of stuff.
Okay. We have 2 questions about Apache Ignite. One is, does it use the gossip protocol? And if that's a real thing, what does it stand for? To communicate with each of the other nodes in the cluster? And does Ignite use dedicated master nodes to perform routing of queries and writes to specific nodes?
Yeah, that's a wonderful question. I think that the one who is asking that has an experience with distributed systems such as Hadoop or similar ones. Speaking about the gossip protocol, no, we don't use that one. Internally, Ignite uses its own implementation of the protocol. And when it comes, there are several. Our networking component consists of the discovery piece that basically lets all the cluster nodes to locate each other within your network, let it be your physical network or your cloud environment. And once the cluster nodes are interconnected through the discovery networking layer, they will be kind of sending heartbeats to each other. They will be exchanging some of the system messages to ensure that the cluster is highly available, that the changes are replicated. The second component of the networking layer of Ignite is so-called communication layer. Every cluster node can open a direct TCP/IP connection with any other participant of the cluster. So that's why whenever, let's say, you have your application, I have my application, and this application is connected to the 3 nodes cluster. When that application sends a transaction trying to update, my bank account, application will know where this transaction record is located. We use it's like partitioning algorithm. We take the primary key of my bank account record. Ignite takes it. It calculates a destination node, a target node that stores the primary copy of my account, and then this application will connect to this cluster node directly. After this connection takes place, that cluster node that stores the primary copy of my bank account will check: do we have any backup copies of the same account in the cluster? Most likely, yes, because that's a distributed system and you want to have at least 1 extra copy of your records. And that cluster node will open a connection, let's say, to the node that keeps the backup of my record. And if you're doing this in a transactional way, like if you're running transactions, then Ignite internally uses 2-phase commit protocol. And with two-phase commit protocol, your application that initiated this transaction will be transactions coordinator. So it will send this command, and then actually it will be performing all the steps: commit phase, prepare phase, etc. And that commit phase protocol ensures that if things go wrong, if let's say any of the cluster nodes goes down while transactions are being executed, it will bring the cluster to the consistent state in real time. I mean, like whether you will have, it will either commit a transaction or it will roll back the transaction. So hopefully I answered your question.
That was great. And I got that one in before Simon could answer it on the internet. Our next two questions are about ReadyNow. Is ReadyNow portable across operating systems? And does ReadyNow and Falcon compare with using LLVM directly?
Right, so ReadyNow profiles being portable, not really, because Zing is only supported on Linux on Intel architectures, so it's portable across the same Linux. It's portable across different versions of Linux, but not any more than that. There are limitations as well in terms of when we use compile stashing, because obviously you need the same architecture that the code was compiled on. So there's limitations there. The second question was LLVM versus or using Falcon versus LLVM directly. What we get there is we've seen some very impressive results in terms of the code that's generated for C++ code. And there was an Apache project, I can't remember which one it was off the top of my head, where they did some work where they hand coded some of the IO intensive work in C++ and then compared the code that they got from using the C++ compiler against what they got from the JIT compiler. And when they looked at the code they got out of Hotspot, obviously there was differences. But when they looked at the code they got from Zing using Falcon, the code they got was identical. So we actually had a 50% improvement over Hotspot by doing that code in the same way through the IO sections.
Okay. Our next three questions belong to a category that I would like to call, how well does Azul test across OSs? The first question is, how does it work in an embedded device with an ARM architecture? The second question is, have you tested in a constrained container like Kubernetes? And the third one is, do you know if anyone's using Zing in Kubernetes in prod?
Right. So first question is easy because we don't support ARM for Zing. We do support ARM for Zulu, but not for Zing. I assume that's what the question is about. Yes. So the second part of that is, does it work in constrained environments like Kubernetes? The answer to that is yes. We did, originally we had some issues related to the use of the Zing system tools that did need a bit more configuration and tweaking. But now that we use the different way of doing our memory management by using Linux system calls directly rather than having to use Zing system tools, it just works in exactly the same way as any other JDK within a container. So that's fine. We can do that. So yes, it definitely works within Kubernetes and in Docker. In fact, we have Docker images of Zing that you can get from Docker Central and stuff like that. I'm not sure if we have any customers who are using it in production in a Kubernetes environment. I'm pretty sure we do, but I can't think of anybody off the top of my head who's doing that.
Yeah, it's tough as a vendor because you only hear from people when they have problems. If someone tried something and it was fine, they're never going to tell you about it.
I know we have lots of people who are using it in a container environment. So somebody's got to be using Kubernetes because there's very few people who aren't using Kubernetes if they're using a container environment.
So here's I can probably just confirm that Azul virtual machines are definitely used in Kubernetes environments, because Simon, it's fair to say that Microsoft Azure cloud environment uses Azul by default. And whenever you are deploying any, let's say, Java-based application with Azure Kubernetes services, then by default you will have Azul, kind of Zul, right?
Well, we need to be a bit careful there because the Microsoft Azure uses the Zulu version of Zulu JDK rather than Zing.
Okay. We have a few more questions. I just want to remind everyone who's listening, if you want to ask a question, now would be an awesome time to put it in the chat. Our next question was an interesting one. I wonder if it makes sense to use Falcon plugged into GraalVM so I can get the benefit of a good compiler and good native code cross-language integration.
Yeah, so that's an interesting approach, because obviously with Graal, the big advantage with Graal is the idea of the native executable. But the problem with that is that you don't get the level of performance once you've started executing the code, because you don't have what you can do with the JIT compiler in terms of speculative optimizations. You don't have the fact that you're aware of exactly what the machine is doing, all of the profiling information and so on. And I know that the people from Graal will tell you, well, they have profile guided optimizations and things like that. But I guess technically, yeah, it could be an interesting thing to try, but that's an awful lot of work, because effectively you'd have to sort of join the two of them together. So you would have initially running Graal created native code, and then you'd have to recompile that as the system is running into LLVM generated code.
Our next question is from way back at the beginning about garbage collection. Is marking the header atomic?
Yes, absolutely. Yeah, because I saw this one in the thing. So because the way it works is that when you want to reference an object, you ask the JVM for the reference to that object, and the JVM will not give you the header or the object, the object header will not give it to you until it has processed it. So in effect, the marking is atomic from the point of view that you will not be able to use that object header until it's been marked. Now, even if you have another thread that's running in parallel, and so let's say we have a situation where you reference the header, it does the test and jump, it goes into the handler, and then whilst you're in the handler, somebody else comes into that, looks to the same object header. We're smart enough to have figured that out. So you still won't be able to get access to it, because we don't set the bits until after we've done the marking. So the marking is marking is an atomic operation. So we can guarantee that, and we can guarantee that even if you've got multiple threads going at it, it'll all work. Okay. So short answer is yes, it is atomic.
Glad to hear it's safe. Speaking of safe, is it safe to use the UAT profile in prod?
Yes, absolutely. If we're talking about ready now, then it's completely safe to use the profiles in production. We have lots of people doing that. And as I say, the thing with the profile is that it's essentially a list of classes that we need to load at startup, a list of classes we need to initialize at startup, and then a set of information that we feed into the JIT compiler ahead of when you start the application. So it's completely safe to run.
I'm down to the last two questions. A reminder to our audience, if you have any more questions, be sure to ask them in the chat. Our second to last question probably is, does Zing Falcon use the JVM CI?
Yeah, it does. Because JVM, I'm trying to think when JVM CI came in, was it 9 or 10? I can't remember. I think it was 9. Yeah, so we have used that as part of it. There's more to it than just the CI, but we do use the CI as part of our interface, yes.
Okay. And our last question, how does Zing play with static and dynamic app CDS?
Yeah, at the moment we don't use those because of what we've done with Ready Now. So that's been our focus initially. App CDS was only contributed by Oracle as open source to OpenJDK, I think in JDK 10. I know we're looking at that as a way of improving the way that Ready Now works a little bit further, but at the moment we're not using it directly.
I thought the answer was going to be different when I saved that for the last question. So I'm going to ask a different last question, because I want the last question to be a nice, happy, positive one. What is your favorite thing about Zing or Zulu?
What is my favorite thing about Zing or Zulu? Oh, that's a tough question, that is. I think my favorite thing about Zing is just the way, yeah, I think my favorite thing about Zing is the way that it just eliminates the problem of garbage collection latency. It's just, you know, it just makes it go away. So you don't have to worry about like garbage collection pauses anymore. So there's none of this tuning this and tuning that. There's none of this trying to build zero GC frameworks or anything like that. You just don't have to do it. You just go, okay, I'll just, you know, allocate objects, let the thing, it's how, you know, the problem just is solved. So yeah, I think that's my best thing for Zing.
Cool. And with that, I'd like to turn it back over to Rodrigo for any closing remarks and, of course, for the announcement of the prize.
Perfect, perfect. Thank you, Jean. Thank you. I think if you answer the survey, Francesca, do you have the list of winners?
Hi, Rodrigo. Yes, I do have a list of winners. So we have 3 winners tonight. So the first winner will be Andrew Chen, and you won the book Designing Data Intensive Applications. Our second winner is Nowl Koimer, and they won Database Reliability Engineering. And our third winner is Tomas Jimenez, and they won Database Internals. So the 3 winners, I will be emailing you with the link to the book. Congratulations to everyone, and thank you for joining our talk tonight.
All right, thank you, Francesca. So, all right, thank you everyone who watched the presentation tonight. My last comment here, June, we have at least 3 events here on the NYJavaSIG, live and free. And how will you find out about these events? Here, follow us on NYJavaSIG on Twitter. Follow us, you'll be the first to know about the events. Okay, we have 3 events. One will be about Java language, one about machine learning, and one of a very popular framework used nowadays. So 3 events in June. Follow us on Twitter and stay up to date with everything that's happening at NYJavaSIG. With that, we can end our presentation tonight. I would like to thank you very much, Dennis. Thank you, Simon. It was an amazing presentation. A lot of things. I learned a lot from the presentation. I would like to thank you both.
Thank you.
Thanks.
All right. Thank you. Have a good night, everyone.